Hi. So in this subsection today, we're going to discuss differentiation and integration of Fourier series. So I will start with integration because this is an easier result. So assume integration. So assume I have f is a PC function. It's only piecewise continuous function. And g is antiderivative. Is one of the antiderivative is, well, and g an antiderivative of f, an antiderivative of f, i.e. g prime equal to f. And the question is to do what? And so assume Fourier series of f at x is equal a0 over 2. I will say a0 of f because now I have two functions plus summation from n equal 1 to infinity an of f cosine n x plus bn of f sine n x. And the question is find the Fourier series of g at x. Now if you remark, now g is continuous. The antiderivative of a piecewise continuous function is a continuous function. And g prime, which is equal to f, is pc. So this implies that g is pc1. So the Fourier series of g definitely converge. Though we don't know, we don't have a theorem. Well, we know, but you don't know. We don't have a theorem. Fourier series of g converges for all x. We don't have a theorem about convergence of f, of Fourier series of f. In fact, it might not converge for every x. Okay. The second thing, yes, this is what I want to say. The second thing is I cannot justify switching integral and infinite sum. I mean, you might think, well, let's just integrate the sum and then do the integral of the sum is the sum of the integral, and this is not correct. Okay, we cannot just switch integral for the sum. We know that the integral of f plus g is integral of f plus integral of g, but I don't know that the integral of an infinite sum is equal to the sum to the infinite sum of an integral. We're going to discuss this later in the course, in fact, in the next subsection. So how to do this? So how, given the Fourier series of f, how to find the Fourier series of g? Now, case 1, a0 of f equal to 0. Now let's see what does a0 of f equal to 0 mean. So consequence, this means that that f sub 1, 0 equal f sub 1, which is equal to 1 over pi integral from minus pi to pi of f of x dx equal to 0. This implies that that integral from minus pi, that 0 is equal to integral from minus pi to pi of x dx, but f is g prime, which is integral from minus pi to pi of g prime of x dx, and this is equal g of pi minus g of minus pi. So the conclusion of this case is that g of pi is equal g of minus pi. Okay. Now I need to find a sub n of g, and I need to find a sub n of f, and a sub 0 also. So a sub n of f, by definition, is f comma 1, which is f comma cosine n x, which is equal to 1 over pi integral from minus pi to pi of f of x cosine nx dx. Now again, I use that f of x is g prime of x cosine n x dx, because f is g prime. And now I use integration by parts. So this is u prime, this is v, integration by parts. And you get 1 over pi uv, which is g of x cosine n x minus pi to pi, minus integral from minus pi to pi, u, g of x, times the derivative of cosine nx, which is n sine nx with a negative sign. So this implies that this is 1 over pi g of pi minus 1 power n minus g of minus pi minus 1 power n plus n times 1 over pi integral g of x, well, integral from minus pi to pi, g of x sine nx dx. But g of pi equals g of minus pi, and this implies that a sub n of f is equal n b sub n of g. And this is b sub n of g, yes, because this is nothing but g sine nx. And this implies that bn of g is equal an of f over n. Okay? This is where here I use that g of pi equal g of minus pi. So this is crucial. Okay? Now similarly, b sub n of f equal 1 over pi integral from minus pi to pi of f of x sine nx dx. And now I use integration. I plug in minus pi to pi. I replace f by g prime of x sine nx dx. Integration by part. This is 1 over pi g of x. This is u prime. This is v sine nx from minus pi to pi minus integral from minus pi to pi g of x n cosine nx dx. But sine n pi is equal sine minus n pi equals 0. I don't care about g here because the sign will make this vanish. So this will be minus n times 1 over pi integral from minus pi to pi of g of x cosine nx dx. And well, so you get bn of f equal minus n. Now this is g cosine nx minus n an of g. And this implies that a sub n of g equal minus b sub n of f over n. So the Fourier series, so if the Fourier series of f at x is equal, now a0, I don't have an a0, this is 0, is equal summation from n equal 1 to infinity of an of f cosine nx plus bn of f sine nx, then the Fourier series of g at x is equal, well, a0 of g over 2, it's a constant, yes? I don't know what's a0 sub 0 of g over 2, plus summation from n equal 1 to infinity of a sub n of g cosine nx plus b sub n of g sine nx, but this is equal a0 of g over 2, I didn't calculate it, plus summation from n equal 1 to infinity. What's a sub n of g? It's minus b sub n of f over n cosine nx plus, this is a sub n of g. What about b sub n of g? Well, this is sub n. B sub n of g is a sub n of f, a sub n of f over n sine n x. But maybe I will write it in a little bit different way so that you notice what I did here. So a sub 0 of g over 2 plus summation from n equal 1 to infinity a sub n of f times sine n x over n plus b sub n of f times cosine n x over n, and I have a minus. So look at this one and look at this one. What's the difference? Here I have a sub n of f cosine n x, and then it becomes a sub n of f sine n x over n. But sine n x over n is an antiderivative of cosine n x. Now what's the antiderivative of sine n x is minus cosine n x over n. So it is as if I integrated term by term. I justify the term by term integration using something different. Yes, I use just the definition. So I didn't prove that I switch integral and sum. I just calculated each coefficient and it turned out to be as if I integrated term by term. Now what is a sub 0 of g? A sub 0 of g is just g comma 1. And this is, I will have to calculate it, minus pi to pi, g of x dx. I mean, this plays the role of a constant because you have an antiderivative. What's the antiderivative of x? It's x squared over 2 plus a constant. So every antiderivative has a different constant, and this is where the constant play. Okay? So example. So we have f of x equal x, and the Fourier series of x at x is summation from n equal 1 to infinity minus 1 power n sine n x, sine n x over n, and I have 2 and I have minus 1 power n plus 1. This is I already calculated, and the question is find Fourier series of x squared plus 1. Okay. Now I have Fourier series of x is equal summation from n equal 1 to infinity 2 minus 1 power n plus 1 sine n x over n. Okay. Now I want x squared plus 1 without redoing the calculation. So how to get from x to x squared? I just integrate. So this implies now the function f of x equal x is pc. Yes, it's pc. So I can integrate. So this implies by from the above Fourier series of x squared over 2, I just took an antiderivative, is equal a0 of x squared over 2 plus summation from n equal 1 to infinity of 2 times minus 1 power n plus 1. So as if I integrate term by term, I just justified. What's the integral of sine n? It's minus cosine n. So cosine n x over n squared. And this will be the antiderivative of sine n x. Is this true? Let me. Sorry about that. So the Fourier series of x squared, which I'm just checking the Fourier series of x is correct. No, the Fourier series of x is 2 times minus 1 power n. No, this is correct. Sorry. Sorry, I have a mistake in my notes. So let me just double check that everything is fine. So now you take the antiderivative of sine. This is minus cosine. So you get here a0 of x squared over 2 plus summation from n equal 1 to infinity 2 times minus 1 power n cosine nx over n squared. And let me check something. So this is a Fourier. So this implies what? This implies there's a Fourier series of x squared is equal, by linearity, of a0 x squared over 2 plus summation from n equal 1 to infinity of 4 times minus 1 power n cosine nx over n squared. And this is something you calculated in one of your tests, yes, the Fourier series of x squared. Let me check that you got the same formula. Sorry, because I found a mistake in my notes and I need to make sure that you are getting the correct answer. Yes, it's correct. Okay. So this is the Fourier series of, but now Fourier series of x squared. Now you have a0 x squared over 2. This is a0 of x squared, the whole thing, over 2, plus summation from n equal 1 to infinity 4 minus 1 power n cosine nx over n squared. Okay. Now what about the Fourier series of x squared plus 1? The Fourier series of x squared plus 1 is equal to the Fourier series of x squared plus the Fourier series of 1. This is linearity. And this is equal. Now what's the Fourier series of 1? It's 1 because it's just a constant. It's already a linear combination of cosine and sine and a constant. So this is a0 of x squared over 2 plus 1 plus summation from n equal 1 to infinity 4 minus 1 power n cosine nx over n squared. So I still have to calculate a0 of x squared. This is 1 over pi integral from minus pi to pi of x squared dx, and this is equal to 2 over pi integral from 0 to pi of x squared dx, which is equal to 2 over pi times pi cubed over 3. And this is equal to pi squared over 3. And this is equal pi squared over 3 plus 1. So the Fourier series of x squared plus 1 is pi squared over 3 plus 1 plus summation from n equal 1 to infinity 4 minus 1 power n cosine nx over n squared. By the way, you could have calculated this constant from the very beginning, okay? Just to tell you so that it doesn't keep it till the end. Fine. Now what if, so case a0 of f different than 0. I will do this as an example. So I already know that the Fourier series of x squared from above is equal pi squared over 3 plus summation from n equal 1 to infinity of 4 minus 1 power n cosine nx over n squared. This is from above. Okay. And now the question is calculate Fourier series of x cubed. So it seems that I will have to integrate, but I here have a constant. But notice that Fourier series of x squared, I bring the pi squared over 3 to the other side, minus pi squared over 3 is equal summation from n equal 1 to infinity of 4 times minus 1 power n cosine nx over n squared. But now, this is the same as Fourier series of x squared minus Fourier series of pi squared over 3, the thing. Yes, because the Fourier series of a constant is just a constant. But by linearity, this is a Fourier series of x squared minus pi squared over 3. This is equal, now I got summation from n equal 1 to infinity 4 minus 1 power n cosine nx over n squared. Okay. And now I can integrate because here I don't have an a sub 0. So this implies that Fourier series, now this is PC, of x cubed over 3 minus pi squared over 3 is equal to, well, when you integrate you get plus x is equal a sub 0 of x cubed over 3 minus pi squared over 3x over 2 plus summation from n equal 1 to infinity. You integrate term by term, 4 minus 1 power n sine nx over n squared. And this was already over n squared, so this is over n cubed. Okay. Now let's calculate a0 of x cubed over 3 minus pi squared over 3x. Now this is equal 1 over pi, integral from minus pi to pi, x cubed over 3 minus pi squared over 3x dx, which is equal to 0 because this is an odd function. So you get that the Fourier series of x cubed over 3 minus pi squared over 3x is equal to summation from n equal 1 to infinity 4 minus 1 power n sine nx over n cubed. And now, but I want the Fourier series of x cubed. So now again I use linearity. This is the same as Fourier series of x cubed. Let's write it 1 over 3 Fourier series of x cubed minus pi squared over 3 Fourier series of x is equal summation from n equal 1 to infinity 4 minus 1 power n sine nx over n cubed. And you get that the Fourier series of x cubed is equal pi square Fourier series of x plus summation from n equal 1 to infinity 12 minus 1 power n sine nx over n cubed. But I already know what the Fourier series of x is. Okay, this is pi square summation from n equal 1 to infinity minus 1 power n sine nx over n. And I think now let's go back and see the Fourier series of x. So I have here 2, I have here plus 1 plus summation from n equal 1 to infinity 12 minus 1 power n sine nx over n cubed. Now this thing is the Fourier series of this PC1 function. So I know that this thing converges. And this is the Fourier series of x. So I know that this sum converge, and now I can then combine the sums. So this is pi squared summation from n equal 1 to infinity of the sum of these 2 minus 1 power n plus 1 over n plus 12 minus 1 power n over n cubed sine nx. Okay, and this is the Fourier series of x cubed. So if you have a0 of f, what do? You bring it to the other side. You bring it to the other side. You write it as a Fourier series of one PC1 function, and you continue. Okay, and PC1. Now what about differentiation? Okay, so let's see. I know Fourier series of x is equal summation from n equal 1 to infinity 2 minus 1 power n plus 1 over n sine nx. Can I differentiate term by term? If you differentiate term by term, so it's a Fourier series of 1 equal term by term summation from n equal 1 to infinity 2 minus 1 power n plus 1 over n. What's the difference sine nx? N cosine nx, which is equal summation from n equal 1. But what's the Fourier series of 1? It's 1. So is 1 equal Fourier series 1 to infinity 2 minus 1 power n plus 1 cosine nx? The answer is no. Why? Notice that the limit as n goes to infinity, well, you wouldn't know this. Notice that for x equal to 0, the right hand side is summation from n equal 1 to infinity 2 minus 1 power n plus 1 cosine, well, 1, which diverge. Okay? And even for x equal 1, this diverges because the limit is not 0 as net n goes to infinity. And by N-stern test, this diverge, okay, for x integer, let's say. I mean, you should, if x is just a number, if x is just a number, then the limit of a cosine x, well, in general, the limit as n goes to infinity of cosine nx, well, this thing, you should be careful about it, how to. I mean, if you fix your x, you can always find n going to infinity, such as it goes to 1, such as it goes to minus 1, is different than 0, let's say. It does not exist for every x, even for x equal to 0. So if this is different than 0, and this implied by N-stern test from 2 to 1, the right sum diverges. Because this does not exist, so the whole limit here is different than 0. I mean, this is different than 0, so the whole limit is different than 0. Then this is not correct. So what happened here? I mean, my function, I'm differentiating now a function that is piecewise continuous. The thing is, when you differentiate, you are losing regularity. When you integrate, you are, because if a function is, for example, C1, when you integrate it, you get a function that is C2. So it's even a better function. But when you differentiate, you are losing, I mean, you are losing smoothness of your function. So you don't know even that if you differentiate, is my function x a good function to differentiate to start with? No, my function x is not a good function. Why? Because I'm not taking only x, I'm taking the 2 pi periodic of x. So, and then when I'm differentiating this, I'm getting that this is a function 1, and now this is the integral for x between minus pi and pi, and then I extend it periodically, and I get the whole thing. Okay? So what do I need? So theorem, when this work, and the proof, exercise, and do this exercise, it's as the theorem of integration. So you should do it step by step. And please do it, okay? Let f be a PC2 function on minus pi pi, and f of pi equal f of minus, well, no, sorry, you want to differentiate. So if you want to differentiate, you don't need only this. Let f be a PC2 function on minus pi pi such that f is continuous on minus pi pi, and f of pi equal f of minus pi. So this implies what? F of pi, it means that the f tilde is continuous on R. So I have a function continuous here, but these two are the same. So when I extend, I get a continuous function. What's f tilde? Is the periodic extension. Then the Fourier series of f prime is obtained by differentiating term by term the Fourier series of f, i.e. if f of x equal, well, if Fourier series of f is a0 over 2 plus summation n equal 1 to infinity a n cosine nx plus b n sine nx, then the Fourier series of f prime will be 0, so I'm going to put here, plus summation from n equal 1 to infinity minus n a n sine n x plus n b n cosine n x. Okay. And this means what? So this means that a sub n of f prime, the coefficient of f prime, is the same as n b sub n of f, and a b sub n of g prime, which is the coefficient of f prime, sorry, which is the coefficient of sine n x, is minus n a sub n of f. And this is very easy to prove, integration by part, exactly as we did for integration, and I will emphasize on this, prove it. Okay? So this means if I have the Fourier series, so if I have the Fourier series of x4, integrating Fourier series of x4, now I draw x4, it's something like this, but it's continuous here, it's continuous here, so the periodic extension is continuous everywhere. Okay, then the Fourier series of 4x cubed is obtained by differentiating the Fourier term by term, the Fourier series of x4. But differentiating term by term the Fourier series of x cubed, we shall not expect to obtain the Fourier series of 3x squared. Why? Since f of pi is different than f of minus pi, where f here is x cubed. This is x cubed. Well, it's continuous inside, but this is f of pi, this is f of minus pi, and this leads to the fact that the periodic extension will not be continuous. Okay? And that's the end of this section. So we're done with all the operation. We're done with the property of the Fourier series. And now, in the next part of this chapter, we're going to start discussing a new kind of convergence. Let's not say new, a strong kind of convergence, which is called uniform convergence. And this will help us answering our original question. If you recall what our original question was, how to deal with, how to get that the solution I constructed to the heat equation, in fact, is this infinite sum is in fact a solution. So that's the end of this section. Thank you.